Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And in this video we're going to take a look at a very powerful rule when we're testing infinite series for convergence, known as the ratio test. Here we're taking a look at an infinite series n factorial divided by n times 3 to the n, and we're trying to determine if this thing is convergent or not. And one really useful tool when you start to see exponential or factorial quantities inside of your series is the ratio test. This is an important one. And it's based a little bit on the geometric series rule there, where in a geometric series we have this thing called the common ratio. And if the common ratio magnitude is less than 1, then we state that we know that the series converges. So here we don't have a common ratio, but what we do is we take the limit of the ratio of a term and the one before it, and we see where that's trending. So the way we express that is the limit of the absolute value of a sub n plus 1 divided by a sub n. So ultimately, if we determine that limit, one of three things can occur. We can either have that limit come out to be less than 1. So there we're saying, okay, it's not a common ratio, but we see that the limit of this thing as the series is unwinding is less than 1, which means that yes, we are multiplying by something less than 1, and yes, this is going to be convergent. If that limit gives us a value greater than 1, that's the ratio test proof of divergence. And then if you happen to run a ratio test and you get a quantity of 1, the answer is that it's inconclusive. And what that means is you probably shouldn't be using the ratio test at all. If you try the ratio test with things like algebraic functions that would be best done by like a limit comparison test, that's what's going to happen to you. So let's go ahead and do the test now. And so in order to do that, we want to set up our limit. The limit as n goes to infinity. Now the first time you do this, if we just follow the definition, it says, okay, we're going to have this absolute value, and it's a ratio, a sub n plus 1 over a sub n, but the series itself, by definition, is a fraction, so we get this big, messy looking compound fraction, which is going to be a sub n plus 1. We're putting n plus 1 in anywhere we see n in our series. So we have n plus 1 factorial divided by n plus 1 times 3 to the n plus 1. So that's a sub n plus 1 on our numerator. And then we divide that by a sub n, which is the series definition, explicit formula, n factorial over n 3 to the n. So we're trying to determine this limit. Now the way that we actually get that done, and once you do one or two ratio tests, what we end up where we usually start is we say, well, if I'm going to have the ratio of two fractions, why don't we just multiply by the reciprocal of a sub n rather than writing it in this original form? So we're going to do that. So it's n plus 1 factorial divided by n plus 1 times 3 to the n plus 1, multiplied by the reciprocal of a sub n, n times 3 to the n divided by n factorial. And so you can, with practice, you can just go ahead and start canceling things. The reason why the ratio test works with exponential and factorial factors is that lots of stuff will cancel and you'll get to your limit pretty quickly. But let's just rewrite it this time here and show what we do. Typically we pair up the ratios of the common types of factors. So I would take the factorials, n plus 1 factorial over n factorial, and then I would take the algebraic factors n over n plus 1, and then I would take the exponential 3 to the n divided by 3 to the n plus 1. So these are the three kind of typical things that you're going to see when you're running a ratio test. Now in the case of factorials, when you take a ratio of factorials, lots of stuff is going to cancel usually. And if I have n plus 1 factorial divided by n factorial, the n factorial cancels and all I'm left with is n plus 1. If you have an algebraic factor, we're going to take that limit. Ultimately, we usually take that by a ratio test, like from the pre-calc version of the ratio test as n goes to infinity. we could do that. This factor would have a limit of 1 as it stands. And then in the exponential case, 3 to the n cancels and we're left with 1/3. Now we do get kind of a special trick here on this one. Because I have a factor of n plus 1 left over from the factorial, I could cancel that with the n plus 1 in the denominator if I wish to. That doesn't always work out that nicely, but here we can do that. So ultimately we're going to take the limit as n goes to infinity of the absolute value of n over 3, which is a limit of infinity, which is greater than 1, obviously. So this is a divergent case, and we've proven by the ratio test that our series is divergent. And you'd really be, with all the other types of convergence tests defined up to this point, you'd be hard-pressed to formally prove that that is a divergent series without the ratio test. And it turns out as we move forward, there are lots and lots of series that are defined with the help of factorial and exponential factors. So the ratio test becomes a very, very important convergence test as we're dealing with these infinite series. If you'd like to learn more about convergence testing and infinite series or calculus in general, you can find those on my calculus books available on Amazon for a really nice price. And also don't forget to subscribe to the channel. Till next time, I'm P. Clark.